This video is going to cover section 12.3 on the regression equation. So at the end of the last section, we saw scatter plots that showed the direction or the correlation and the strength of a relationship between variables. And though data rarely fit a straight line exactly, we often have a set of data whose scatter plot appears to be close to a straight line. So it can help us to understand our data and to make predictions if we draw a line on our scatter plot that represents the relationship. And this is called a line of best fit or a least squares line or a trend line. And the mathematical process to do this is called linear regression. We only do this if one of the variables helps to explain the other variable. We can use a regression line to predict values of y for a given value of x. And the line could be a curve or a straight line. We're only going to be dealing with straight lines in this class, but remember, it's possible for other shapes to occur. So some vocabulary. The least squares line, our trend line in Excel, is the best linear equation representing the points of the scatter plot using the least squares criterion. And we use the notation y hat equals a plus bx for the least squares line. So that little caret, that little arrow over the y, we call that y hat. The correlation coefficient, R, is a numerical measure of strength and direction of the linear association between the independent and dependent variables. So if the slope of the trend line is negative, then this value will also be negative. The coefficient of determination is R squared, and that's the square of our sample correlation coefficient, R. So we have some data here. This is example 12.6 in your book. And in a random sample of 11 statistics students gave us this data, and X is the third exam score, which was out of 80 points, and Y is their final exam score out of 200 points. And we want to know if we can predict the final exam score of a random student if we know their third exam score. So our third exam score, X, is our independent variable, and our final exam score, Y, is our dependent variable. We're going to make a scatter plot in Excel, and we're going to look to see if the data seems linear. And if it is, we're going to add a trend line using the Add Chart Element menu. So open up the Excel sheet in Canvas. Our first tab here is exam scores. Again, remember when we're making a scatter plot, we want to have our X's in that left-hand column, or what we think is our independent variable in the left-hand column, and our dependent values in the right-hand column. So we're going to highlight everything, including the titles at the top of the columns, and we're going to insert a scatter plot. So here's what the scatter plot looks like. I'm just going to do that because I grabbed the wrong thing. I'm going to sort of scooch it a little bit so that we can see the whole thing. So I'm going to change my title. This is going to be Final Exam Scores versus Third Exam Scores. This is one way to say that final exam scores are along the y-axis and the third exam scores are along the x-axis. Remember, we can always add our axis titles, and that would be, and this might be something useful to say that this is our third exam scores, and maybe we want to say here out of 80. Right? So you're always trying to think, like, what does your audience need to know to understand what you're trying to tell them? So then this would be final exam scores out of 200. Because they do seem to be very different. So it is kind of nice to see that they have, they're out of a different basis. They're not percentages, they're just raw scores. All right. So I think that the horizontal axis has good marks. I think the vertical axis has good marks. And now I'm just looking at the data. And those points do seem to potentially have some sort of linear relationship. So to add the trend line, I am going to go, so I got to click on my chart so that it's highlighted. So now I'm in my chart design menu. And over here, I can add a chart element. And all the way down at the bottom, I can see the trend line, and I can choose the one I want. Now we're working on linear trend line, so I'm going to click on that one. And it's added that dotted blue line to my chart. my graph. So I'm going to click on it. You know, again, there's lots of different ways that you can have this look. Those blue dots, I don't think are really obvious. So I like to change them over here to color. I'm going to go over here to color, and I'm going to do a solid line. I'm going to change the color to red, and it didn't change it. Oh, it's the style. Here we go. I just think that that's a little more easy to read around the blue points to have a solid red line, but you can change it to any color or style that you want. Again, remembering that you want your audience to be able to see what you want them to see. And then the other thing I'm going to do is down here at the bottom under this trend line options, I'm going to display the equation on the chart, and I'm going to display R squared value on the chart. Now, it kind of put it right over the top. It's hard for me to read it, so I'm just going to click on it and drag it so that I can see it a little more easily. And you'll notice that they write that equation sort of in a more traditional y equals, in this case, bx plus a format, whereas our book and the slides are doing y equals a plus bx. Addition is commutative, so you can write that in any order. It's the same thing, but just remember when you're being asked to talk about the a and the b values that if you're looking at Excel, they've switched places. And then we have our R squared value here. So here it is after we did the scatter plot in Excel. We've already done that, so we know that it looks linear. So we added the trend line. So we selected the scatter plot that we created. We clicked on chart design at the top of the screen. We added the chart element from the upper left corner, and we chose trend line from the drop-down menu. We selected more trend line options at the bottom, and we chose solid line, and we picked a color, something that stands out. We chose red. And then we saw three choices. We clicked on the picture of the bar graph so that a new dialog box opened, and we chose linear. We chose display equation on the chart and display R squared on the chart. So when you're doing this in class for homework on any other assignment, make sure you have all those things. So I wrote on the chart, you can select the equation and drag it where you would like to be. So you can always adjust all those little things so that it looks the way you want it to. So here it is again after it's been done. And we see that the equation for the line of best fit, now Excel doesn't write it this way, but we are going to talk about it as y hat equals negative 264.38 plus 6.108x, and R squared is 0.7308. So in the slide, I wrote it in the traditional way. Excel has it in its own way. So if we all tried to draw a line of best fit by hand, which is what you often will do first before you use Excel, everyone's line would be slightly different because we can't all be perfect and we're human. So the method of finding a line that would be the same for all of us on the line of best fit is called the least squares method. And in that way, or in that method, each point of data on the scatter plot is of the form x comma y, we know that, and then each point on the line of best fit has the form x comma y hat. So y hat is an estimated value of y. It is the value of y obtained using our regression line or line of best fit, and it's not necessarily equal to any y value in our data. So points on our line may not be data points. As you can see, the blue dots are the data point, and only some of them are actually touching the red line. But the line of best fit always goes through x bar comma y bar. And remember, x bar is the mean of the data, so the sample mean of the x data. Y bar would be the sample mean of the y data. So the line of best fit is always y hat equals a plus bx, and a then equals y bar minus b times x bar. So if you were going to calculate it by hand, you would figure out x bar, y bar, and you would calculate that, but you would need to know what b is. B is our slope, and that's equal to r times s sub y divided by s sub x, where S sub x is the standard deviation of the x values, and S sub y is the standard deviation of the y values. So you can start to see that if you're going to do this by hand without Excel, that you have to do a lot of math to come up with these things. So we know how to find the standard deviation of the y data. We know how to find the standard deviation of the x data. And then R, the correlation coefficient, we're going to look at that equation in a minute. But you need the standard deviations, you need the means, you need the correlation coefficients, and then you could write the line of best fit. And if we did it this way, everyone's line would be the same versus if we all just drew one by hand. So we, when we're doing this kind of work, we always want to do the scatter plot first to make sure that it does look like there's a linear relationship between the variables. We're hoping for like a strong linear correlation, but even if there's a weak one, we can still do a line of best fit. If there does seem to be a linear relationship, then it makes sense to make predictions for y given x within the given x values of our sample data. It doesn't always make sense to try to do prediction outside of those x values because we've only used those x values to come up with the equation. So we could use the line to predict the final exam score for a student who earned a grade of 73 on the third exam, but we wouldn't use it to try to predict the final exam score for a student who earned a grade of 50 on the third exam, because 50 isn't in between the x values that we have, which were 65 to 75. So anyone's third exam grade between 65 and 75, we can estimate or predict their final exam grade. But if you got below a 65 or above a 75, our prediction wouldn't be as accurate and we might not want to do it at all. So slope. The slope of the line B describes how changes in the variables are related. It tells us how the dependent variable y changes for every 1 unit increase in the independent variable x on average. And we always have to think about our slope in the context of the situation represented by the data, like being able to say, oh, it increases by this much, when what goes up by 1. You need to know what those variables stand for to really understand your slope. So in our example, where y hat was equal to negative 264.38 plus 6.108x, we had a slope of 6.108. And that meant that for every 1 point increase on our third exam, the final exam is going to go up by 6.108 points on average. So our correlation coefficient R is another indicator of the strength of the relationship between X and Y. It was developed by Carl Pearson in the 1900s, and it's a numerical measure of strength and the direction of the linear association between the independent and dependent variables. So here is the equation to calculate R, and it looks really busy and really hard, but it's really not, because remember that sigma notation just means we're adding things up. When X is next to Y, it means multiplication. So we're looking at N, which is the number of data points we have, and then X and Y comes from those individual points that we have. So we could do all of those calculations in Excel with columns and stuff, and we could figure out R by hand, but we're going to let Excel do that for us. So if you suspect a linear relationship between X and Y, then R can tell us how strong that linear relationship is. So the value of R, the actual numerical value, is always between -1 and 1. The size of it indicates the strength of the linear relationship between X and Y. So values of R close to -1 or close to +1 indicate a strong linear relationship between X and Y. And a rule of thumb is that R is considered strong if it's greater than 0.7 or less than -0.7. If R equals 0, there's likely no linear correlation. But again, you always want to look at the scatter plot because your data could have a nonlinear relationship or it could look horizontal. So then there is a relationship, it's just not this linear one that we're looking for. If R equals 1, then we have perfect positive correlation. If R equals -1, we have perfect negative correlation. And in both of these cases, all of the original data points lie on a straight line. In the real world, this doesn't really ever happen, but in theory it could. So what does the sign of R tell us? A positive value of R means that when X increases, Y increases. And when X decreases, Y tends to decrease as well. So that's like that positive slope that we saw when we were talking about slope. A negative value of R means that when X increases, Y tends to decrease. And when X decreases, Y tends to increase. So that would be a negative correlation and it would have a negative slope. The sign of R is the same as the sign of slope B of our best fit line. And just remember that strong correlation doesn't suggest that X causes Y or Y causes X. We say correlation does not imply causation. So just because two variables have a strong relationship doesn't mean one causes the other. So the coefficient of determination is R squared, and that is what Excel actually gives us. And so it is the square of the correlation coefficient, and it's usually stated as a percent. So side note, if you have R squared from Excel and you need R, take that number and take the square root, and now you have R. But in the context of the data, R squared represents the percent of variation in the dependent or predicted variable, Y, that can be explained by variation in the independent or explanatory variable, X. So now we have a couple of new words. So dependent is predicted, independent is explanatory, like it explains the other one, we're saying. Kind of sounds like causation, but it's not. And then 1 minus R squared represents the percent of variation in Y that is not explained by variation in X using the regression line. And that's the scattering of the observed data points about the regression line. So looking at our previous example where we had the line of best fit equal to Y hat equals negative 264.38 plus 6.108X, our coefficient of determination was R squared, and that was 0.7308. Square rooting that gives us a correlation coefficient of R equals 0.8549. So that is bigger than 0.7, so it is a significant correlation. And what the coefficient of determination is telling us is that approximately 73% of the variation in the final exam grades can be explained by the variation in the grades on the third exam. And that means that 27% of the variation, 1 minus the 0.73, in the final exam grades cannot be explained by variation in the grades on the third exam. So that's how we talk about and interpret the coefficient of determination, R squared. And that's the one that Excel gives us. So one more example, just to go through all the steps. We have a random sample of 10 professional athletes where X is the number of endorsements the player has, and Y is the amount of money made in millions of dollars. We're going to do a scatter plot of the data. We're going to use regression to find an equation for the line of best fit. We're going to draw the line of best fit on the scatter plot. We're going to talk about what is the slope of the line of best fit and what does it represent, and what is the y-intercept of the line of best fit and what does it represent. So if you go back to our Excel sheet and you go to the endorsements tab, you can see we have number of endorsements and amount of money made. Highlight everything here. Insert your scatter plot. So this time the title I had up here didn't have that Y in it, so you might be happy with what that is. You might still want to say amount of money made versus number of endorsements. We might want to add our every time I want to go in here and I want to be able to add the titles here, but I can't. So I'm going to go back to the chart element where I know where it is. So that's the primary horizontal. So that's the number of endorsements. And I'm going to go over here to this axis, add the vertical title. And this is amount of money made. And you could say, I think it's in millions too. So your reader knows what they're looking at. So when I look at the scatter plot, it looks to me like it's pretty linear. And so we're going to go ahead and we're going to go to add chart element and we're going to add our trend line. We can put linear on right away. We can go or straight to more trend lines. We're going to go, again, I like to make it red. I like to make the style, that's the wrong one, dash type. I like to make it solid. And then I want to go over here to what looks like a histogram. And I want to put on display equation on chart and display R-squared value on chart. And you can fool around with all the other things too to see what it looks like and see if it helps you with what you're trying to say, the story you're trying to tell with your statistics. Okay, and so here we have our equation and our R-squared value. So if you wanted to, you could find out what R equals, right? So I know that it's going to be the square root of, I put an extra parentheses, 0.9577. My R value is 0.978621. So that's close to 1. So this is a pretty good correlation. It's a strong positive linear correlation in this data. And then R squared we can see is 0.9577. And we'll talk about that in a second. But 95.8% of our data of the amount of money made, of the variability in the amount of money made is due to the variability in the number of endorsements. Okay. So if we go back here, here's the scatter plot with our trend line, the equation, and our R-square value added to it. So what is the slope of the line of best fit and what does it represent? So up here we can see it's the number in front of X and it's approximately 1.99. And it means that for every one endorsement deal, those are the X variables. So every one endorsement deal a player gets, how much money they make goes up by 1.99 million each year. What is the y-intercept of the line of best fit and what does it represent? So that's going to be the other number we have here, the 2.2336. And that represents how much a player makes with no endorsement deals. So if X was 0 and there was no endorsement deals, the player would make a little bit more than $2 million. So that's the end of the section 12.3 on the linear regression and the line of best fit, also called a trend line in Excel.